The xt diagram of a simple harmonic motion is shown in the following figure here. The motion is described by x of t, or x, the position as a function of time, is equal to the amplitude times the cosine of the angular frequency times the time, plus the phase constant. What are the amplitude, angular frequency, and initial phase of the motion? So we can directly figure out the amplitude by looking at the picture. If you look at this, you'll see that the peak of the simple harmonic motion is when x is equal to 1 meter. So the amplitude of this motion is 1 meter. Now we need to figure out the angular frequency. So if we look at this graph, we get that the period of this motion is equal to 1 second. And we know that the angular frequency, denoted by omega, is equal to 2 pi over the period. And in this case, the period is simply 1 second. So the angular frequency is simply going to be 2 pi. And we can actually say that this is about 6.28. And it has units of radians per second. Radians per second. And this angular frequency is basically the same thing as angular velocity from circular motion. So I'm going to write down about 6.28 radians per second. So that's our angular frequency. I'm actually going to keep it precise, the 2 pi radians per second. But either way works here. This is just a little less precise than 2 pi. Now that we have figured this out, the question asks us for the initial phase of the motion. This one is going to be a little bit harder to derive, but we can think about where the wave is when it's at its initial position. And in this case, the initial position is going to be equal to 0.5 meters. Also note that this is not an answer. I'm just writing this down here for now. And that is equal to the amplitude times the cosine of the angular frequency times the time. And this is the initial time when time is equal to 0. So the initial time is when we start using this equation, and the time is equal to 0, plus the phase constant. So the initial x is going to be equal to a times the cosine of simply the phase constant, since when we initially plug in the values for this function, so the initial time is when t equals 0 seconds. This whole part will cancel out, and we're just left with the phase constant. And then we get this equation here, which we can solve for the phase constant. The phase constant is then solved by the inverse cosine of the initial position divided by the amplitude. You can just divide both sides by amplitude and take the inverse cosine. And then we can plug our values in. The initial x position is 0.5 meters, and the amplitude is 1 meter. So this is simply the inverse cosine of 1/2, which is 60 degrees, or pi over 3 radians. But we're not done yet, because there is another solution, and that is negative pi over 3 radians. And if you think about like the unit circle, and like pretend this is the unit circle, and you have like your 60 degree here and negative 60 degrees here, or pi over 3 radians and negative pi over 3 radians. The cosine value is going to be the horizontal component of this triangle. And these two are both the same. So there are actually 2 possible solutions. So we actually can't tell which one the phase constant is just yet. So we actually need to solve for that. So I'm going to say that the phase constant is currently equal to pi over 3, or minus pi over 3. And this is in radians. And this is not the final answer. We're going to have to solve for this using another method. So we can check by looking at the velocity of the object in simple harmonic motion. If you remember, the velocity function is given by the derivative of the position function with respect to time. So this, you simply take the derivative with respect to time of the position function with time as the input. So this is the derivative with respect to time of the amplitude times the cosine of the angular frequency times the time plus the phase constant. So now if you use the chain rule and everything, you should get that this derivative is equal to the negative of the angular frequency times the amplitude times the sine of the angular velocity or angular frequency times the time plus the phase constant. And this is our expression for velocity as a function of time. So I'm going to rewrite the velocity as a function of time is equal to minus omega a sine of the angular frequency omega times t plus the phase constant. And this is our function for velocity. Now, again, we suppose that we have an initial velocity, and that is equal to negative omega a sine omega t. And this t is going to be the initial time plus a phase constant. And again, the initial time is going to be 0 seconds. So this whole part will cancel out again, leaving us with just the phase constant. So we're left with the initial velocity is equal to minus omega a sine sine of the phase constant. And now, if we solve for the phase constant, we get that the phase constant is equal to the inverse sine of the negative of the initial velocity of the object in simple harmonic motion divided by the angular frequency times the amplitude. Now, if you look at this, you might notice that it's unsolvable because we don't know what the initial velocity is. But the thing is, we actually don't need to. We just need to look at the sine of this variable, or sorry, the sine of the initial velocity of the object in simple harmonic motion. And if you remember, the velocity is the rate of change of the position. And since this is a position time graph, the velocity is simply going to be the slope of any point of this graph. So you can take the slope at any point to figure out the velocity at any point. So if we look at where our initial position is, if we take the slope of this, you will see that the initial velocity is going to be positive because the initial slope is positive. If you take the slope at this point here, I can't really draw on this, but if you take the slope here, the slope is positive. So the initial sign is positive. And since the initial sign is positive, these two will not cancel out. So we've calculated omega, the angular frequency, to be positive, and the amplitude is also positive. So if the initial velocity is also positive, there will be nothing to cancel out this negative sign here. So this whole expression will be a negative value. And so you know, the inverse sine of any negative number is still going to return a negative value. So the inverse sine of any negative number will give you a negative value. And this is because, again, going back to our little unit circle, the sine is the y component of each little coordinate here. So the only places where you're going to get a negative degree is down here. So that is why it would always have a negative value here. So if the inverse sign of this negative value returns a negative value in radians, then this would have to be the only possible answer. So this is not the phase constant, and the phase constant is going to be negative pi over 3 radians. And that is how you would solve this problem here.